determine whether the following series converges or diverges, and if it converges, we want to find its sum. So you want to recognize that this series here is one where we have a rational function. It wouldn't be geometric. Perhaps as telescoping, to see that, we'd have to partial fraction decompose this, and it turns out that, yes, it is. It's telescoping. How does the partial fraction decomposition work? Well, currently it's in one fraction. We want to break it apart into two fractions, where we have some a over 3n minus 1 and some b over 3n plus 2. So we have to find the values of a and b that make this work. The a fraction needs to be multiplied, both numerator and denominator, by 3n plus 2. The b fraction needs to be multiplied, both numerator and denominator, by 3n minus 1. And then that will give you the old numerator of 9. This is true for all n, even more than just the integer n's. And we're going to pick n smartly so that we can get one of the variables to cancel out and only have to deal with the other one. So let's choose n equals 1/3. Why? Because it'll kill the b term, and we don't have to worry about a. When we plug a 1/3 in, the coefficient on b will be 0. The coefficient on a will be 3, so it turns out that 3a equals 9 means that, of course, a equals 3. We do it all over again. Next, we would like for the a coefficient to be canceled out. So if 3n plus 2 is 0, that means n is negative 2/3. Plug that in. The negative 2/3 causes the a coefficient to be gone, and it causes the b coefficient to be negative 3. But when you divide by that negative 3, you get the fact that b is negative 3. And we have our two constants. So we take our original series and rename it to be the series on 3 over 3n minus 1 minus 3 over 3n plus 2. Now, you could pull out the 3's, but what often happens when you do that, you forget to put it back in. Let's just say we leave it in there. And our job is to find the sum of this series by looking at the partial sum sequence. So we let n equals 1 and see what we get for that. N equals 2, we add that. N equals 3, and on until n equals n. So we plug a 1 in and we plug a 2 in. Maybe you need to go one more. Let's plug a 3 in. Whatever you need to see when cancellation happens. And then let's plug in and the guy before it. Maybe we might even need the guy before that. So when we do this, this simplifies. How does it simplify? Well, we have this n equals 1 case. And that gives us 3 minus 1 in the denominator, which is 2. 3 plus 2 in the denominator, which is 5. So 3/2 minus 3/5. We have this n equals 2. N equals 1 is that guy. We have this n equals 2, which is the next guy. And with that one, we're going to plug in and get 6 minus 1, which is 5. 6 plus 2, which is 8. This is the n equals 2 case. N equals 3. We get 9 minus 1, which is 8. 9 plus 2, which is 11. So we get 3/5 minus 3/8 and 3/8 minus 3/11. And here's what I want you to do. I want you to go until you see your first cancellation. And that's going to occur right away with these first two terms. This minus 3/5 and this plus 3/5 are going to cancel. What I want you to do next is write down the same number of terms at the end. So it took 2 terms to get cancellation. Then write down your 2 terms from the end when we have n minus 1 and when we have n. And so the n is just a repeat of what you have inside your summation. When you put n minus 1, be careful to distribute. We get 3n minus 3 minus 1 for a total of 3n minus 4, 3n minus 3 plus 2, and that'll give us 3n minus 1. So we have those last guys. And what you should do is make the cancellation that you get at the beginning be mimicked by the end. And then here's what you're going to do from that point. The thing that's changing is the denominator. Any denominator that's larger than that should be canceled out. the 3/8 are going to cancel out. Now, you don't have the next term, but the 3/11s are going to cancel out, and everyone in between is going to cancel out. From the other perspective, at the end, any denominator smaller than 3n minus 1 should cancel. So this 3n minus 4, you didn't write the term that's right before it, but that's going to cancel. And another tool you can use is the fact that whatever's left over from the beginning, you should have the same number of terms left over at the end. And so we get this collapsing, this telescoping, and we're left with just one term in the beginning and one term in the end. Let's go to the next slide to see how we're going to then calculate the sum by doing the limit. So we started with the original series, we partial fraction decomposed it, we're looking at the sum, and what we have for our partial sum S sub n sequence, that is 3/2 minus 3 over 3n plus 2 with all of the collapsing. So what happens as n gets big? Well, of course, this 3n plus 2 gets big, and 3 over something that's very large is very small. This term will go to 0, leaving us with the answer of 3/2. That's going to be your sum. Although you're adding up infinitely many terms, it adds up to this finite number 3/2, which actually was part of the first term, not exactly the total first term. Okay, great.